Great. All right. Well, let's go ahead and get started. So I'm Brandon Atkinson from Weave, working on the DevX team there. And then Carson Anderson is also here. We are the co-chairs for the Utah Go user group. So just to introduce the meeting today, I was going to take this out, but I decided to leave it in as a reminder. A lot of us are usually in person and not on Zoom, so make sure to mute yourself so that we don't have a lot of background noise going on. I don't know how good your computer's microphones are, but they're probably good enough to pick up background noise. So make sure you do that. Jobs and hiring as always, Utah Forge Slack. If you are looking for people to hire, or if you would like to find a job, this is a great resource. There's a lot of good stuff going on in that Forge Slack. So feel free to jump in. And if you need help finding that or getting info for that, feel free to hit me or Carson up after the meeting today. We'd be happy to help you find that. If you want to speak, feel free to reach out. There's this paper call link. Oh, there we go. Thanks, Todd. That's the link. So there's this paper call. If you want to submit like a formal paper, but you can just reach out to me or Carson, or just reach out on the Forge Slack. That's usually how we do things. Nash just sent me an email, and so we're happy to work through it that way. But this link is available if you're more comfortable with that. And we pretty much accept everybody who wants to speak. We're happy to kind of workshop around what you feel like you can present. So if you don't feel like you have a full hour or whatever of stuff that you can talk about, sometimes we do multiple talks in a session. We want to get people up here speaking. We want to get a diversity of speakers. So definitely come to us if you're interested. We'd love to help you be part of this community. So that's kind of all of the prelude. So we'll turn the time over to Nash Foster, who's going to talk to us about building high-performance global scale blockchains in Go. I'm going to stop presenting and turn the time over to you, Nash.
Yeah. Just a second. Just getting my. This is how I do this. All right. So I'm presenting. So yeah, my company is called Silvermint. We used to be Pyrofex, and we started working on this project that eventually became Silvermint, and back in 2018. My co-founder and I noticed we pivoted into the blockchain space in 2017, and having both been at Google and worked on large-scale systems for a number of years, by 2018 we recognized that there were some core problems in terms of scale that needed to be solved, and so we started working on it, and then it got funded in 2020. Late 2020, and then in early 2022, we raised a seed round, and have been working on it ever since. And when we raised our seed round, we looked around to decide what language to run it in. We decided to write it in Go, which now has a cute little animal logo, thanks to John DeGose, who should be forgiven for his skull-loving ways. So what our goals, I'm going to go over our goals, talk a little bit about our project first, and then I'll just sort of dive into some of our experiences with Go. You guys probably have a lot more experience with Go than I do. I have been programming for 30 plus years, but Go is something that's new to me since last February, I think is when I've made my first commit in Go. So I would be more than happy to learn where I'm wrong about various things over the course of this presentation. So If you have anything to say, just shout out. I don't mind being interrupted. Just unmute and holler at me. So what were we trying to do? So what we wanted to accomplish was something that didn't exist in the blockchain space and still really doesn't, which is that we wanted a blockchain that could handle global transaction scales, which means hundreds of thousands of payment transactions per second. And we wanted to continue to be able to handle that on a decentralized infrastructure with a trustless computing environment, as opposed to what a lot of projects have since done, which is to just go back to essentially the pre-blockchain world and do everything in a centralized way and pretend because you like sprinkle crypto on it that means that it's secure and trustless and all this other kind of stuff, the way that Bitcoin is. And so even today, we feel pretty confident that our project is going after the real brass ring here, compared to everyone else. What we specifically want in that regard is we want transaction processing to be as fast as real world payment networks. Visa, MasterCard, Amex, Discover, all the big payment card industry settlements are 1 to 2 seconds at most. Whereas the big layer one cryptocurrencies still to this day have confirmations that take 10 plus minutes and settlements that don't complete for hours. Obviously, that's not viable for splitting the lunch check or buying a cup of coffee. And, until you can do that, you're really not viable as a payment platform. So we want to fix that and settle as fast as Visa with as many or more transactions in our network throughput. So some considerations for how to build a decentralized system like that. Because the system's trustless, every node in the network has to do the same amount of work. So if you want to be fast for end users, you have to be really fast locally. The workload's not, like in a general large scale computing environment, the cluster size works for you, where you can split the work up amongst different computers. And as the more computers you add, the less work each individual one has at the same workload. That's not the case for blockchain. And blockchain, larger network sizes tend to work against you, because of the need for every individual to do the same amount of work requires you to ship the blocks to everybody. It gets overwhelming. Locally, data structures that work great on real world data often suck on blockchain data. We'll see an example of that a little bit later on. But we ended up going back to a lot of really low level computer science stuff to solve what in the normal world would be fairly straightforward problems, but they were made more difficult for us because of the blockchain context. And then you have really heterogeneous systems environments. In a network of a couple of thousand nodes, every one of those nodes is run by somebody different. They have a different sense of what production means. They may or may not follow your instructions. They may or may not know what they're doing. We felt like, and we still do feel, a really strong commitment to providing really well-engineered code that works really well and integrates well with the systems it's meant to run on. And then we feel like if we don't do that, we're going to be in a tech support nightmare and a reliability nightmare, which is not what we want. So, okay. So why did we pick Go? Starting here, so the first thing is that we felt like it was going to be really easy to learn. And this turned out to be totally true. Our whole team started programming in January and February of last year. We've been productive almost from the beginning. We wanted an expressive language, which Go definitely is. More expressive even than I expected. Our server software today is only 23,000 lines of code. Would have been well over 100,000 in C or C++, which I've been there. I don't ever want to go back. Go is fast. A lot of the structures are competitive or much faster than their equivalents in the STL. And it's systems oriented. We knew from watching Kubernetes become successful that there were tons of great tools for building good system software. And even though when we sometimes looked at things, they weren't that mature, we felt like they would either become so or it was not going to be a big deal. And we felt like all four of these have turned out to be true. So in terms of easy to learn, so our team isn't that large. There are something like 8 of us that develop Go. We all managed to learn it, except for one guy who came in knowing it. All of us managed to learn it in about a month and become proficient and productive in under 60 days. There were a couple of things that we struggled with initially, like understanding exactly how interfaces worked, but they were very easy to overcome. And often, once we understood them better, our code productivity improved a lot, especially compared to other languages. Specifically, that interfaces were way easier to learn than the borrow checker. So, I think Go fills Python's niche way better than Python does, especially in terms of ease of use. You can much more easily write fast code. The syntax is less weird. Core libraries have a more standard feel somehow, even while giving implementers more flexibility. I'm not sure exactly why that is. Somebody wants to jump in and explain it to me, that would be love. I would love to hear why, but it does seem to work really well. And so all of the packages on the Go package site are really straightforward to work with. And so in the future, I can see Go doing to Python what Python did to Perl, which would be really cool because I'm tired of Python. Brandon's trying not to laugh. Go seems super expressive to me. Go programs are short, really, really short. I don't understand why they're so much shorter than other programs doing the same thing, but I like it. So maybe you guys have some opinions about why Go is short. I'll take a second to see if anybody wants to unmute and throw out an answer here.
I mean, I'll happily throw out some stuff. I do think that to some extent it's culture. There's a big culture in the Go community towards a very certain style of code, which lends itself, I think, to some of these benefits that you've mentioned. So beyond just language design, which I do think is important, I think that's an aspect that shouldn't be overlooked.
Yeah, it would have to be something that we could inherit, like that our team could inherit culturally without really knowing or interacting with the culture, because literally none of us were Go programmers beforehand. So we have very limited exposure to other projects that were written in Go or anything like that, other than what we see when we Google it on Google. But yeah, I think from certainly from the places where I encounter the Go culture, it does seem like it works pretty well. The only thing that bugs me is not being able to have 2 packages able to depend on each other. I know this is probably wrong of me, but it feels like I want it a lot. So, but there we are. We can work around it. Okay, so in our system, one of the biggest problems for us is making this thing as fast as possible, which I mentioned earlier. And the reason is that if we're going to do, say, 150,000 transactions a second, every single node in the 2,000 node network has to process all 150,000 every second without getting behind, which means we have to be quite a bit faster than most centralized systems, ironically. So a key part of this is conflict detection. In a trustless payment system, you have to know if someone's trying to double spend the same coin, essentially. Coins in our system are represented by something called a UTXO, which doesn't need really to be defined, but it should be thought of as basically a digital coin, because when you spend it, it behaves a lot like a coin. So or a dollar bill or something. So if I've got 20 Silvermint and I give Brandon 10, then the payment transaction that gives him 10 returns 10 change to me. And now there are 2 coins instead of 1. The trick is to make sure that you never accidentally let someone spend the same coin twice, because that obviously lets them make money out of thin air, which is no good. So the mechanism for that in Bitcoin is to totally order all transactions, but that really doesn't work very well when you want to scale up. This is one of the reasons why Bitcoin is so slow. So we instead allow transactions to be processed more or less asynchronously. And in order to detect a conflict, we have an abstract notion called a conflict domain, which mathematically is basically a partition of the transactions into comparable domains so that they can be checked against each other. And that all works really well at low transaction rates, but at 100,000 TPS, you can't be naive and just, check every transaction against every other transaction, because O of 100,000 squared is a big number. So initially we tried just using Go maps. This was workable at up to about 20 transactions a second, but up closer to I guess 2,000 or 3,000 transactions a second, it was too slow, and 100,000 transactions was way too slow. So we started looking for other things. So things we considered, various kinds of prefix trees. None of those give you any benefit if the thing that you're keying on is a hash, because hashes are random and evenly distributed, so the prefixing doesn't do anything. We looked at special sorting algorithms. That turned up a bunch of papers where the researchers were calling their work the hard problem of search. That didn't sound like something I wanted to have to solve. So as interesting as the reading was, we didn't go that way. We did try to parallelize comparisons on NVIDIA GPUs with CUDA. That was actually quite a bit slower than the Go map, interestingly. Eventually I figured out that this particular kind of thing that we were doing was not in the target workload for NVIDIA GPUs, but we tried it anyway. We did try C++ STL maps, which were way worse than even the GPUs. I think that's because they're red-black trees instead of hash tables, which was a little surprising to me to find out, but I guess it makes sense if you're a C++ guy. I don't know. What we ended up settling on was something that surprised me. It was this really old algorithm that I hadn't heard about since I was a teenager, which is basically an open-coded linear hash table. We wrote that in native Go, and it was blazing fast. It was faster. We didn't even bother trying it in C because it was so fast. So snapshot of the algorithm. So we made the assumption that key 0 and value 0 aren't valid because that's true for hashes. And we all further made the assumption that keys are random, or at least random looking. Since ours are hashes, they're as good as random, and this is true. And then we built tables where the key is k bits long, and the values need the restraint on the values is that they need to be small. In our case, we started with pointers, eventually converted them to integer or to interface references, but these are only 16 bytes of data stored in each entry, which is pretty small. Keeps even 24-bit, even tables that are keyed to 24 bits are still reasonably, they're big for an individual table, but they're something that you can put a bunch of copies of them on a reasonable sized cloud machine, and it'll still be okay. So we do a fixed allocation of 2 to the k values, usually during startup. Most these tables are reused, so you insert a bunch of keys to detect all the collisions, and then you just zero it out and use it again. And the way that the insertion algorithm works is that keys are inserted at their natural address. So if your 16-bit key is 0, it's inserted at element 0. There isn't one. But, whatever your 16-bit key is, it would just go into literally that item in the array, and store the value in the array. And the keys are derived from just taking chunks of the hash and using that as the key value. If you find that there's something already resident in that array index, you just keep moving up until you find a free spot. I should have sort of been more clear here. If you find that you've switched from your key value to another key value, then you sort of move a bunch of stuff to make a free spot. So there's some fiddly bits into exactly how it works. But the net effect is that after you've inserted all of the keys in your collision set, all of the items that have the same key value are contiguous with each other, and you can simply scan the array one time to find all the collisions in the collision set. The result is that we were able to detect collisions across millions of keys in under 100 milliseconds, which was our time budget for this, which is absolutely plenty for our use case. False positive. Sorry about that. False positives can be made extremely rare with this because our keys are derived from hashes. The cost for that is simply memory. So if you can tolerate false positives, and you can, so the flip side is also kind of true. If you can tolerate false positives, you can reduce the amount of memory needed. But ironically, smaller tables are slower because false positives are typically slower. Well, at least for us, they're much slower to deal with than if you can get all of the items into a single table without very many collisions. So in the future, because this is central to performance, we might rewrite it in assembler, C, but only if we're forced to. The Go implementation's only 100 lines of code, and it's really, really fast. It's definitely not a bottleneck right now, so I don't worry about it. And I'm really pleased that we were able to find something that was so easy and small to write, that did the job really well for us in native Go, as opposed to having to do something much more complicated, which would have made the project more difficult to work with. One of the other performance examples that we've noticed is a big difference in the performance and the ease of use between mutexes and channels. So we sort of started writing our Go code that looks a lot like Python or C code might look, and we ended up using a lot of mutexes for synchronization. But then we ended up spending a lot of time chasing mutex contention, which really sucked. In particular, because there's not particularly great tools for finding mutex contention that are native to Go, and Go mutexes have a behavior that we observed pretty frequently when things got busy, where they'll start off doing Go mutexes start off in a kind of busy wait kind of scenario where you attempt to acquire the thing, and if you can't acquire it, you just keep looping until you do. But once some things have waited for a few hundred milliseconds or a half a second, they switch to using a queuing mode. And for us, some of the early algorithms we wrote when mutexes end up in that queuing mode, we noticed that the performance just dropped off a cliff in terms of throughput, which really stunk. So lately, we've been using channels a lot more, and they're fiddly to code, as asynchronous programs always are. But they do seem to offer much smoother performance. So if you can build algorithms as a pipeline where you're sending data down channels and processing it as it goes, and then you kind of get it out at the end of a pipeline. That seems to be really nice and smooth, and it seems to schedule really well on the Linux scheduler onto, machines that have lots of cores. So, we're often working right now in the cloud with machines that have 32 to 64 cores, which is a good, it's plenty. And there seems to be good performance when things can kind of land on a couple of cores and work well together. We don't have a huge amount of experience with it, but we're migrating more and more algorithms to it now, and it seems like a big improvement. I am kind of curious whether anybody else has had this sort of experience and what you guys might have, conclusions you might have drawn from it.
Yeah, I
Usually
mean,
across the network for us. Oh, go ahead, Carson.
oh, sorry. Yeah, I agree. I think actually mutexes and channels are both things that are fiddly and to be kind of really wary, because both of them, if you don't really like, I don't like to use mutexes at all unless they're in some place where they're really narrowly scoped and self-contained, because you can just so easily get yourself into a fail state. And definitely if you're like constantly coming back and checking a mutex and trying to like reacquire a lock, I think channels are way better. But yeah, I always try to hide those as much as I can. Anybody that's like, Go channels are great, and when you need them, and they're very useful and they're really performant, but they're almost always something you want to not have be front and center, and like you want to be hidden behind a library that kind of abstracts it away.
Yeah, fully agree with that.
So it's interesting that it's massively more performant though.
Yeah, I don't know. I think it's, well, for us so far, it's smoother, which means like it doesn't seem to degrade suddenly the way mutexes occasionally do. So obviously, like if you get into deadlock, your mutex is, like you degrade it to 0. But we also see a lot of times if there's contention, we can have a lot of work come in, and then all of a sudden something that was running in 170 milliseconds, all of a sudden it's taking 89 seconds to run, and we're like, why? And the only thing we can find is that there's just mutex contention, and the queue's never empty, and that kind of thing.
Yeah, I see when you do a lot of profiling, you see mutexes in big boxes a lot of time for your profiling. Like they tend to be points of contention.
Mm-hmm. Yeah. Yep.
It looks like Mariah just dropped a question in the chat. If you are building web services, how often are you sharing memory across Go routines?
Well,
We
that was
aren't.
not referring to blockchain usage. I'm just saying a lot of people in the area build web services, and so you wouldn't use channels as your main source of memory sharing for web services. In blockchain, that's a different story, right? So you end up in a whole different, like a whole different set of semantics and design orchestration. My comment is, that's kind of, if you're a lot of companies in the area that use Go do web services, so you don't end up with the whole design stuff of channel. But I agree, Todd's comment kind of addresses mine. I think I think channels are a fantastic use case over the mutex for this, so that you aren't doing as many IO operations. You're just doing orchestration. So I think it makes sense to me.
Cool. I'm reading Todd's comment.
At Mariah.
Oh, I see. Yeah. Yeah, right. There's at the center of our of our server is a large directed acyclic graph that contains essentially all of the blocks that have been issued since whatever the event horizon is for the server. So that DAG is big and it's being constantly modified as blocks come in. Our blockchain every node issues a block about once a second. So unlike normal blockchains where you have one node that issues a block and then it becomes someone else's turn, we don't do leader election. We're completely parallelized. And so in a cluster of 1,000 nodes, you have to be able to add 1,000 blocks to the DAG every second and then process all the transactions in them at the same time. And our goal is to try to finalize all those transactions in about 2 seconds. So there's quite a bit of shared memory for different processes when you've got, for example, 1,000 active TCP connections on the receive side as well as 1,000 active TCP connections on the send side, and they're all trying to either access the DAG or manipulate it in some way. It's quite a bit of shared memory, and you're right, it's not the same kind of thing as a web service, really. It's a very different kind of network service that we have to deal with. So this may end up in the long run being more. I may end up having more to say about this in a year. Once we've played with channels more, but at this point it seems better and smoother. And smoothness is a really big thing for us, right? Because we need certain algorithms that run in our server have to run with real-time time budgets that can't be exceeded, or it starts costing the person money who's running the node. So we're trying really hard to make sure that everything runs extremely fast. Okay, so one of the things that we like about Go is that it's really systems oriented. As I mentioned earlier, I knew some of the Kubernetes guys when they were at Google, and then sort of came out and started that company and that project. And I watched them use Go really effectively. A big part of our problem space is making software that's reliable, even when the systems administrators kind of go out of their way to screw up deployments. Go gives us a lot of time back. When the amount of code you have to write is so much smaller, you get your work done faster, and we're not endlessly debugging nonsense. So we're able to spend more time on the system stuff than we otherwise maybe would. It also includes a ton of tools that make things easier. I mean, like command line parsing is pretty good. I wish it wasn't quite so wonky, but it feels pretty easy to use. So we're able to make servers work the way people expect them to pretty quickly and easily. There's a lot of easy ways to interact with the Unix environment. We even have good signal handling in our server, which that's pretty cool. TCP libraries were especially a bright spot. I really liked writing code for the TCP/IP stack in Go. We end up doing a lot of wire level encoding because our network messages all have to be signed, blocks have to be signed, so everything has to be written to the network in the exact same way every time if it has the same data. Otherwise, the signatures will be broken. And so that would, in a lot of languages, that would be hard. But in Go, it's just tedious. It's not hard at all. It just takes time to get it right. And but the way you get it right is easy to repeat once people understand what they're doing. And yeah, Carson says the flag package isn't great. I totally agree. We've been using Viper for our stuff, and that is pretty good. It has some rough edges, but generally speaking, PFlag and Viper I have found are pretty good improvements to the flag package.
Yep.
Okay, so here's some things we haven't really figured out that are hard and annoying. Debugging memory leaks, it really sucks. The memory profiler sort of works. We lean on Prometheus a lot, but we find it hard to know how large a structure is, and we're worried about counting bytes because it all seems slow, so we don't do it. In particular for structs that have contention. Other things that are hard, C1. We spent a week and a half this last week debugging a memory leak. We think we got it yesterday at like 9 o'clock at night, but it's not, we're not sure yet. So I'd be curious to find out how you guys identify and handle memory leaks in production servers, because any help that we could get would be awesome.
I wish I had
For-
any smart answers. Maybe Todd, do you have a smart answer?
I might have. Let's not put it up there.
Okay.
let's keep the expectations low.
An answer.
A lot of people, especially here, are definitely working with web servers where everything kind of gets cleaned up afterwards, except for like contexts or whatnot that are shared across all requests. So that's usually handled by the framework where you're doing work in a long-standing server. We've done a lot of things that are more like network available queues, but it's like keeping a lot of state, and then it has to share that across requests. Like several things might ask for the next thing in one of 20 queues. And basically anything that's like allocating memory, we've really had to be very strong on what allocates and what deallocates, kind of becoming the memory manager. There is the new stuff coming out in Go for memory arenas that will probably alleviate some of that, where you can just say, look, this is the memory arena you get to play in for your thing. And then you can kind of isolate this module or whatever is using this memory, and we've only allocated this much. So if it ever goes over that, we will have errors that say this thing is misbehaving. It kind of narrows down where your memory leak is going to be. And that's usually a lot easier to reason about when not a lot of things are going to be touching that. So hopefully that is helpful for the future, but it isn't helpful to any of us right now. So
When does that come out?
it's in beta right now.
Interesting.
So who knows? It could be slated for the next release. It could be 2 or 3 releases from now. But you
That's
can use it in
exciting,
beta
Simon.
if you have like a compiler kind of option. I think is the option is the way you use it.
Okay, I'll look into this. This could be useful. Because yeah, one of our biggest problems is actually just finding where the memory is where we'll see it, and it'll be like, 20K a second, and we're like, man, it's like there's a block being leaked somewhere, because blocks are about 20K usually. And we'll be like, there's a block being leaked somewhere every second. We can't figure it out where it's going.
But everything uses the block, right?
I mean, they're supposed to, well, the way that it's supposed to work is they get put into the DAG and then they're used. So for a 1,000 node cluster, we typically have about 5,000 memory resident blocks. And then the remainder of the DAG is offloaded to disk. So it's sent down to SSD, and it sits on disk in a little database that we wrote, so that it doesn't pollute the memory space. But yeah, I mean, you'll often see something like that, and we just can't figure out where it's being allocated and where it's, what's got hold of it, which is annoying.
It does remind me of the old C days before you had like Valgrind doing nice stuff for you, and
I know, right?
but it's in a garbage collected language, so it's even harder to get at that without doing a lot of extra corralling. So I feel your pain, but hopefully the memory arenas will help.
Yeah, maybe it will, honestly. Yeah, I guess so that's pretty much it for me. I'm Nash Foster. I'm the CEO of Silvermint. You can find me on Twitter at NashEFoster. So we included some links in the slides here. Hopefully you guys will get a copy of it. I think if I click share, you guys can get a copy of it. And then I probably
Nice.
have to set permissions to anyone with the link. So yeah, so you can go find our code, and if you find bugs in it or want to just make fun of us, you can join our Discord and give us a shout out. Yeah, so any questions or comments?
No, we'll go ahead and give our digital. If we all clap enough, it does a big explosion. So
Oh, does it?
yeah,
Can I clap for
there it goes.
myself?
There we go.
Ah, nice. That's the best.
Yeah, it's way more fun than it should be.
I did have
Yeah.
a post talk question.
Sure.
I would love to hear a little more details. You mentioned that you didn't have very good success with trying to use CUDA and running your algorithms on the GPU, and alluded to some more depth there. I would love to hear a little bit more detail about what the problem was with using the GPU and why Go was able to outperform.
That's a good question. Let me see if I can page in all the details of my 2 weeks in Cudaville. So part of it is undoubtedly that I have relatively limited experience in CUDA. I have some. I've done some projects with it, which is one of the reasons I thought it might be a good fit. But I'm not an expert. The first problem is that the algorithm needs to basically like do the Cartesian product of about 100,000 items. So it's creating pairs where each pair is unique. And even for CUDA, the memory footprint, if you sort of just represented those, was large, and the computational overhead to make all the pairs would be large. So naive algorithms didn't work. And then generally speaking, the way that algorithms that run well on CUDA seem to work is by being able to break them up into sort of linearly independent chunks. So if you're doing matrix multiplications and stuff like that, there are sophisticated ways of breaking the problems up into smaller problems and then reassembling them efficiently. And literally none of them applied to us. It was one of those things where I would find an algorithm and be like, oh, that looks promising. And then I'd finish the paper and be like, oh, all the caveats are like, why this doesn't apply to your data, Foster. The things that we ended up trying were basically ways of making use of the CUDA's extremely fast cache layer between the main RAM, and trying to find ways of getting the conflict detection to run basically all in cache with like one big load and then grind on it a bunch. And I think we actually did manage to do it, because by the time that we were done, we were the algorithm we were using was running pretty well. It ended up running about the same time that the CPU would do it with a regular hash table. But to get there, I was flattening the memory bus of my GTX 3090. And so the prospect of telling people they had to buy like, a Tesla card or something like that was not like, I didn't love that as a as a response. And so at the end of the day, the thing is that GPUs just aren't good at building hash tables in the way that we wanted. They're designed to do lots of parallel linear jobs at once, and that's not what we were doing, and so just didn't seem to work out.
Yeah, that's interesting. Thank you.
Yeah, Todd says hashing is the big thing on GPUs. That's only sort of true. So Bitcoin doesn't use GPUs. The blockchain that's famous for using GPUs is Ethereum. Ethereum uses the GPU it's actually, what it's doing is not so much hashing as it is taking hashes that the CPU computes and looking them up, solving problems on a really large data structure. So their proof of work consensus algorithm as of a few years ago was called Dagger Hashimoto. And the idea was that you could take a small seed and hand it to the GPU, and the GPU would generate like an 8 gigabyte data structure out of it. And then you could answer queries, and you would generate the queries on the CPU and hand them over to the GPU, and it would tell you that they were all wrong, and you would try again. And you could kind of do that at the speed you could move data back and forth between the CPU and the GPU, and at the speed that the GPU could interact with its RAM. So there was a big performance delta between Ethereum nodes that had really fast GPU RAM and those that had less fast GPU RAM or whatever. But I don't know that they were. I don't remember that they were. I don't think the hashing part was actually done on the GPU in any meaningful way. Yeah, as far as memory limits, like the 3090 that I had was big enough to hold all the data points I needed. I just couldn't find a data structure that it didn't really matter. There wasn't an algorithm for making it work that I could find. And I didn't have infinite time. Once I found, and the other thing is that the linear hash table was one of those things that came to me while I was pounding on the GPU. And because it only took 100 lines of code to write, I wrote it up the night that I thought of it, and it worked so dang well. I was like, I'm done with this shit.
Fair enough. Once it works, it's good enough. It's good enough, right?
Yeah.
Especially like.
And it's hard to argue with something that solves your problem in 100 lines of code when you know that every other solution you've got is like 1,000 or more, and you're like, I'm using 10% of the code to solve the problem. 10 times better. There's like, it was good. It worked really well. If you click through on our GitLab, it's in the DAG directory. It's called lht.go. It's a pretty simple piece of code. It's an algorithm that's been around since the 70s, so I don't even want to pretend like I invented anything, what they didn't. I just realized that an algorithm from the 70s was the thing we needed. And it worked.
We all do advent of code a lot in Forge. Algorithms from the 70s are great. I'm not going to go figure it out from scratch. Why would I do that? Cool. Well,
yeah, it made me feel happy that I'd solved it, and stupid at the same time for not trying something that I probably should have learned in my CS 300 class or whatever. But we eventually got there. So, any other questions?
Okay. Well, I'm going to go ahead and stop the recording. And thank you, Nash, for presenting. It's great to hear from you. Lots of interesting stuff.
Thanks for having me. I really appreciate it.